All right, so this is the 2021 BC Calc FRQ. Let's go through and take a look at question one, which is again part of the calculator section. Over here, we have it pulled up. It looks like it's a table, which indicates that it's most likely going to be a Riemann sum kind of question. But let's take a look and see what they have in store for us. So let's choose a color. We'll go with light blue. So they give us in centimeters and some function based off of the, I can only assume radius. But let's take a look. The density of a bacteria population in a circular petri dish at a distance r centimeters from the center of the dish is given by an increasing differential function f. So it's key to note that f is increasing, and we can see 1, 2, 6, 10, 18, yep. Where f of r is measured in milligrams per square centimeter. Values of f of r for selected values of r are given in the table. So they select 0, 1, 2, 2.5, and 4. Cool. And it's actually a pretty large petri dish if it has a radius of at least 4. But let's take a look. Use the data in the table to estimate f prime of 2.25. Using correct units, interpret the meaning of your answer in the context of this problem. So let's take a look over here and let's just try to get a handle on this as well. So imagine for a second that there's actually going to be some sort of petri dish. So let's see if I can actually draw that. We'll maybe do it like this. So there's some sort of petri dish that's there. And what I'm seeing here is that R is the distance from the center. And at 0, the density seems to be just 1 milligram of bacteria per square inch. But as you get a little bit further, let's say what is it? Oh, sorry, this is 2 centimeters. That makes a lot more sense. So 2 centimeters, it's going to be a little bit more dense. And again, it's going to be kind of like this annulus. So like this, it's a circular ring of density. So as you move further out from the center, it looks like the circular ring gets denser and denser. And this kind of makes sense because if you think about it, maybe you swab this right in the center, and then the bacteria culture started growing and it started consuming the agar that was there. And essentially, it started expanding outward from the center. And if it manages to consume everything or it reaches its lifespan, then it just kind of dies in the center, but continually grows outward to form this kind of ring. At least that's the story I've made up in my mind. So in that case, it makes sense, but it's just getting denser as it moves outward. So over here, they just want us to go ahead and actually estimate the value of f prime of 2.25. Now notice, in this case, the input function is centimeters. So as a result, we're taking the derivative with respect to r of this kind of f prime of 2.25. So essentially, you can think of it as derivative with respect to r of f of r, like that. And we're going to evaluate it at r equals 2.25. That's essentially what this statement actually means. So this right here, we should just go ahead and take a secant line from the table using two kind of adjacent points and use that to estimate what the slope of the tangent line would be. Because that's really what this derivative is asking. So we would say, it looks like this will be approximately f of 2.5 minus f of 2 all over 2.5 minus 2 like this. All right, so keep in mind this is a calculator section, so you can use a calculator if you need, but this problem seems easy enough. So f of 2.5 is 10, f of 2 is 6, and then 2.5 minus this is just going to be 1/2, so 0.5. And then as a result, this will be basically 8. And then we can give it the units. So this looks like, again, milligrams per square centimeter. That's what F is. And since we're taking the derivative with respect to R, it would be per centimeter. So it would be milligrams, so mg per square centimeter. So cm squared per centimeter, like this. Uh, is that right? That looks a little awkward, but Yeah, I guess that makes sense. So over here, we could interpret the question as being the following. The What would we say? The rate of growth, right? Or the density, actually. Let me see, what is F? Yes. F is density, yeah. So the density of the bacteria population, uh, 2.25 centimeters away from the center of the dish. I'm just kind of copying what they're saying up here, right? Is increasing uh, at a rate of approximately 8 milligrams. Well, I guess I'll type it out, milligrams per centimeter cubed, right? So would have almost interpreted this as like a volume kind of thing, but again, it is what it is, right? So it's just saying that the density is changing as you change your distance from the center. And that's just going to be your first part. Okay. Also, just keep in mind what the whole idea here is. It's just saying that you've been given a graph of points, right? So if this is your centimeters for your radius, right? So radius in centimeters. And then over here, this is kind of your density, right? Then it's just telling you that at 2, so at 2, it's a certain value, and at 2.5, it's another value. And it gets to 6 and 10. And so there's 1 point and another point, and the function's increasing. So it could increase like this. It could increase like this. It could increase in some sort of combo like that, or it could even just be a straight line. And you have no idea. But it wants to know what the slope is at 2.25. So it wants to know, like, what is the slope of the tangent line at this x coordinate. So like if I were to intersect the graph at this coordinate, what would it be? So if you were to draw it, maybe here it'd look a little flat like this. If it were here, maybe it'd look something like, sorry, like this. And what we're saying is regardless of what happens, you're just going to choose the secant line and say, this is going to be my best estimate without any further kind of information on how it looks like. Obviously, we know that, again, it's increasing and differentiable. So that lets us carry through with this assumption over here. But going back, let's go through and let's take a look. Part B, the total mass in milligrams of bacteria in the Petri dish is given by this integral 2 pi times the integral from 0 to 4 of r, so that's the radius that we have here, times f of r dr. So let's just imagine what actually happened here. Um, Essentially, you have 2 pi r, which is the circumference of a circle. And then at each of these units, there is a certain amount of bacteria on this ring. So just like how I drew in the picture earlier, essentially the density around this circle is going to be the same. They're all going to be dependent upon uh, how far it is from the center. That's why we have a function f. And so if we're saying start with the circle with radius 0, then the circle, and go all the way up until you reach a circle of radius 4, and then kind of sweep around, this is almost like polar, right, interpretation. But if we were to delete it, this indeed does give us the density of, or the total mass of the bacteria, right? So in this case, approximate the value of 2 pi integral from 0 to 4 of r f of r dr using a right Riemann sum with the 4 subintervals indicated by the data. Okay, so they're telling you you want to write Riemann sum. They're giving you 0 to 4. They're saying use this as a first interval, and right Riemann sum would use this height. Use this as an interval. Use this. This is an interval. Use that, and then the fourth interval, and use the 18. All right, so you can kind of visualize it over here. But in B, we'll just go ahead and write out the formula. So if we were to do this, how would we actually go about doing it? I guess, yeah, 2 pi, and then integral 0 to 4 of r times f of r dr will be approximately, and so we're going to approximate the integral, so we just keep the 2 pi on the outside. And we're going to have 4 subintervals. So 1 minus 0 is just 1, right? And then we're going to multiply it by 2. And then over here, we're going to add, I'm going to run out of space. 2 minus 1 is just 1. And then we're going to multiply that by, actually, hold on, let me see. What's going on here? I guess that would be interpreting just the f of r. I need an r times f of r. That's kind of strange. Okay, let me think this through real fast. Yeah, that would normally be an approximation of just f of r. So if I want to approximate this one, I'd have to throw in an extra r. So r would be 1 for the first interval. And then I'd say, what is my f of r going to be? I would multiply it by, over here, 1 again, because that's 1 minus 0. And then I would multiply it by f of 1, which is 2, like this. Yeah, I think that's what we're supposed to do. So this one's kind of atypical. It's different than the other Riemann sums that we have. Also, I'm totally going to run out of space, so I'm going to write this on the next line. So this right here will be approximately 2 pi, and what we said earlier, 1 times f of 1 is 2 times the interval length, which is 1 minus 0, which is 1. And then we're going to add, radius is now 2 times f of 2 is 6 times the interval length, which is 2 minus 1, which is still 1, plus over here, r is 1, 2, and then we're looking at 2.5 multiplied by f of 2.5, which is 10, multiplied by the interval length, which is 0.5. And then the last interval, we're going to have the radius, which is 4, times the f of 4, which is 18. And then we're going to multiply by the interval length here, which is 1.5, like this. I believe that this is how we're supposed to do it. Because typically we're only approximating the integral from 0 to 4 of like f of r dr. But in this particular case, you actually have an r here. So you're not integrating just f of r, you're integrating r times f of r. And so if you were to use a right Riemann sum, this would be kind of your approach. This is actually quite strange, and I will definitely use a calculator for this. So I have Desmos pulled up over here. I'm going to pull this to the side real fast and see what it actually equals. So in this particular case, we have 2 pi. We're going to multiply it by 1 times 2 times 1 plus 2 times 6 times 1 plus 2.5 times 10 times 0.5 plus 4 times 18 times 1.5. And it looks like we have this. So did I type in everything correctly? If so, then yeah. Oh, hold on. What did I do? Okay, well, obviously I typed that incorrectly. This is supposed to be like that. Okay, let me just double check my work one more time. This is causing some problems. 2 pi times 121, 261, 2.5, 10.5, 4, 18, 1.5. Okay, yeah, that looks good. So over here, then 845. Let me just write this down real fast. And again, round to 3 decimal places. So over here, this is approximately 845.088. And then I'll see if they want it in integers or whatnot. But over here, let's highlight the whole thing and then move it back over here. All right, so just like that is fine. And then let's go to this. So yeah, in milligrams of this integral expression, approximate subintervals. Yeah, okay. So then this would be milligrams. and that would be is the approximation of the total mass of bacteria in the Petri dish. So over here, let's take a look. C is the approximation found in part B, so this one, an overestimate or an underestimate of the total mass of bacteria in the Petri dish. Explain your reasoning. So in this case, they're just looking for what the rate of change actually is supposed to be. So in this particular case, let's see. Then I think over here, we're supposed to just go ahead and take a derivative. Let me see if that actually makes sense. Is the approximation in part B an overestimate or an underestimate of the total mass of bacteria in the Petri dish? So we use the right Riemann sum, and obviously this is increasing at an increasing rate. So that's going to be concave up, and because it's increasing, that's fine. Yeah, okay. So let's see. In this particular case, you typically have R times F of R. That stands for the basically mass of bacteria is there, and we're just trying to figure out how this is changing, and then we'll see if that actually has any effect. So if we take the derivative with respect to R of this function, then we'd have to apply chain rule as well as product rule, right? So this looks like derivative of R with respect to R, so that's just 1 times f of R plus R times derivative of f with respect to R, like this. And so this would just equal, yeah, and derivative of f of R, will keep it consistent. So this would be f of R plus R times derivative of f with respect to R. So all I know in this particular case, this term right here is strictly positive, right? Because it starts at 1 and it is increasing. And then the R is also positive because it starts, well, it starts at 0, but it's only going to be 0 to 4. So that's also going to be increasing there. And then what is the dFdr? So the derivative of f with respect to r, they already gave it to us over here. This is increasing. So increasing, hence it is also positive. So it looks like the rate of growth will be strictly greater than 0 because it has all 3 components is positive, so or really 2 components is positive, and that'll be the case here. So in this case, is that right? Does that make sense? Yeah, okay. So in this case, because you're doing a right Riemann sum on an increasing function, if you just imagine it like this, your rectangles, if you're choosing the rightmost points, right, on any sort of increasing function, doesn't matter if it's concave up or concave down, a right Riemann sum on an increasing function will be an overestimate, all right? So over here, we'll write this right Riemann or right rectangular approximation method on an increasing function will lead to an over OVER estimate. Okay, so again, the idea is very simple. Like if you were to integrate f of x dx, and you wanted to know like from 0 to 4, just like this in general, right? You might have a function, and the only thing that you need to assess is whether or not this function is increasing or decreasing, right? If it increases like this, then as you take a right Riemann sum, you can see how each of these rectangles will be an overestimate. And similarly, if it were to go concave down, you're still going to overestimate by using right rectangles, right? So it'll maybe be less extreme of an overestimate, but an overestimate nonetheless. So basically, in these cases, you just want to know, is it increasing or decreasing, which is why you look at the derivative of this function. So previously, if we were looking at our function over here, this thing, then this is our kind of interior function. And we just want to know, is this increasing or decreasing? And so we took the derivative of it, which again provided this, and you had to obviously use context clues and just some analysis, but you could figure out that it's actually positive, and hence we have an overestimate, right? So over here, let's take a look at D. The density of bacteria in the Petri dish for R is between 1 and 4, so 1 and 4, okay, is modeled by a function G defined by that monstrosity, okay? For what value of K, where K is also between 1 and 4, is G of K equal to the average value of G of R on this interval? Okay, so again, this is a calculator question. You're going to have to use a calculator, but essentially they're just saying, can you find the average value for me, right? That's all they're saying here. This is a rather kind of convoluted way of actually stating it, and I think that's what they're trying to do to get you. So I would say in this case, the average value is going to be equal to, and since they're taking a kind of this integral here, or interval from 1 to 4, you're going to take the integral yourself. You're going to say there's a certain amount of area, right? So I think this is my third time trying to draw something like this, but imagine you have something like this, and you were to say this is from 1 to 4, obviously not drawing the scale, right? Then the average value just simply says that the area underneath this curve right here can fit neatly into a rectangle of similar size. And I just want to know the height of this rectangle if it shares the same base, right? And so that's what the average value here is. So you want to find the area of what it is and divide by the base, and then you'll get the height of the rectangle. So in this particular case, we just need to do the following. Average value will equal 1 over 3, so 4 minus 1, times the integral from 1 to 4 of g of r dr, right? So that's going to be your average value there. And we're supposed to find where it occurs, right? So we'll do that as a second step. But over here, we should plug this into a calculator. So let me take this, and let's actually write down G. Hold on one sec. I'm going to lose it. So this equals 1 over 3 times the integral from 1 to 4 of, it looks like 2 minus 16 on a cosine of 1.57 square root of r, n quantity, and then cubed. And I'm, again, just mismanaging my space, but we'll see if we can actually pull it a little bit this way. Yeah, cubed like this. So square root, let me see if I'm cubing the right thing. 2 parentheses cubed, yes. And then another, and then dr. Okay, so let's go ahead, highlight that on the left-hand side, pull it over. Oops, sorry. Highlight this whole thing on the left-hand side, pull that. Oh, why is this so strange? Okay. This is okay. That's fine. They don't want to move together. That's okay. That and some technical difficulty. Okay, I got you. I will wrangle this that way. Okay, and then let's put in a calculator and see what we actually get. So 1/3, obviously we're going to use your graphing calculator and learn how to actually use it before the test. So times, and this will be cosine of 1.57 square root of R. Let's see if Desmos likes that. N quantity squared, like this, and then dr. Okay. Let's see. Did I write everything correctly? 2 minus 16. And this is multiplied by cosine of 1.57. Let me just make sure everything here is correct. Yep, in radians, we're good here. So what is that? 2 minus 16 cosine of 1.57. Oh, it's cubed. Oh, okay. Well, in that case, I almost made a very silly mistake. Let me see if I made anything else. Yeah. 2 minus 16 times cosine 1.57 square root of r and quantity cubed dr. Yeah, that should be good. And I forgot an r over here. So let's fix that part. So that's an r. So this will be approximately equal to how much? Well, this will be approximately 9.875. And I'll move all this back now. 757948. Okay, so let's do that and bring it back over here. So 794875. Okay, so that's basically what it's roughly equal to. And oh, I guess I actually had to find the value of k where this is actually true. So somehow g of k, yeah, somehow equals this, right? So I should probably write this over here. G of k is equal to that. So this is going to be our average value. And G of k is supposed to represent that average value. So we're supposed to find this where k is between 1 and 4. So the only way we're doing that is with our graphing calculator. I think I'm going to just clear it, make my life easier. So in this case, we'll highlight this part. This is my function. We'll say y equals, I really don't like r, so we're going to change to x like this. And then x is supposed to, or sorry, y is supposed to equal 9.875794, like this. And we're supposed to only look at the interval when it's from 1 less than x less than 4. So we're only looking on this interval right here. And it looks like it has one value, which is 2.497. So let's clear this back over here and we'll just write it. This is k will be approximately 2.497. And then going back to the question, it would say for what value of k is equal to the average value, is g of k equal to the average value? So there you go, you found the value of k, and we're good to go. So let's check that with the scoring guideline and see what actually happens here. So over here, let me zoom out. Well, okay, well, that works too. Use the data on the table to estimate that. So over here, f prime of 2.25 is approximately this. Yep, we have that, and equals 8. So 1 point for the estimate. Fantastic. At a distance of r equals 2.25. Okay, so 2.25 centimeters away from the center of the dish. Okay. The density of the bacteria population is increasing at a rate of 8 milligrams per square centimeter per centimeter. Yeah, okay. So again, per centimeter cubed is gonna work out well. This is a really strange one. Always remember, like when you're taking a derivative, figure out what you're taking the derivative with respect to. That'll just directly give you hints as to what your denominator unit should be. So if you're differentiating with respect to the radius, that means you're taking a derivative with respect to some sort of length as your measurement. If you're doing it with respect to time, then you better use a unit of time, right? So just be careful on that. That was really tricky. the units milligrams per centimeter squared per centimeter. Yeah, okay, maybe attach the estimate of this. And if so, do not need to be repeated in the interpretation. Oh, okay. So like basically what they're saying is if you put it here, then you don't even need to try to use that in your interpretation. If units attached to the estimate do not agree with the units in the interpretation, read the units in the interpretation. Oh, so basically, if you interpret it incorrectly in your interpretation, then it doesn't matter if you got it correct up here, they're going to mark you wrong. So apparently that's dangerous. So just I would still probably interpret it both ways, but I would interpret it and just double check that you get it correct in your actual written response. All right. So that's not too bad. Over here, the total mass in milligrams of bacteria in the Petri dish is given by the integral expression here. So use a right Riemann sum with 4 subintervals indicated by the data. So in this case, oof, okay. Let me just see. All right, so yeah, in this case, 1, 2, 3 components, 1, 2, 3 components, 1, 2, 3 components, 1, 2, 3 components. This is a very strange Riemann sum problem. Typically, they only have like the singular function that is in there for you. But now in this particular case, they're having you approximate it with just everything that's there. So again, they're giving you the interval. So you can imagine it would have been if I pull it back, sorry, not this one. 0 to 1, right? So you'll use that interval. But instead of trying to find the Riemann sum for f of r, which I assume a lot of students are going to make this mistake or would have made the mistake, they want you to find it for r times f of r. So luckily for you, because it's a right Riemann sum, you have the value of r and you have the value of f of r. So that's why you have those two units that are there. And then they write it out and they multiply it. And I remember I almost messed this up because I typed it incorrectly. So just be careful with how you enter it into a calculator. The presence or absence of 2 pi has no bearing on earning the first point. So they're saying that some students probably like to do the Riemann sum of just the integral first. So if you don't have a 2 pi, that's still going to be okay. That's cool. A response of this will earn the first point, but not the second. So in this case, you actually need to figure it out. You have to like give a specific value for what it is. A response with any error in the Riemann sum is not eligible for the second point. So again, you have to write out the actual work that leads to the Riemann sum. Completely correct left Riemann sum earns 1 of the 2 points. A response that has any error in a left Riemann sum earns no points. So apparently if you get the left Riemann sum, they'll still reward you with something. And then simplification of the numerical value is not required to earn the second point. If a numerical value is given, it must be corrected 3 decimal places. Wait a sec. I thought they just said that a response of this earns the first but not the second. Okay. What's the second? Simplification of the numerical value is not required to earn the second point. If a numerical value is given, it must be correct. So apparently you don't need to simplify it. Oh, I see. So basically they're just writing this. I think I jumped straight to this form right here, and I didn't actually write out like that the interval needed to be calculated. But this is strange. This is quite a mess of a question. It's tricky. All right. So don't feel too bad about this one. Over here for C, is the approximation found in part B an overestimate or an underestimate? So again, the theory being if you're looking at your integral, you're integrating some sort of function. All you need to do is take that function and take its derivative and then figure out, is it increasing or is it decreasing? Am I taking a left Riemann sum or a right Riemann sum? And then basically, bam, you will be able to figure out whether or not you have an overestimate or an underestimate just like that. So over here, product rule expression for this, that's fine. Again, College Board prefers the prime notation. I prefer the DFDR notation. Over here, f is non-negative. It is increasing. And then this over here, they just directly say the entire term is positive on this interval. And so therefore it's strictly increasing, hence right Riemann sum is an overestimate. Yeah, you might want to write Riemann sum approximation, but I think that RAM should still get you the point. I think it's like common enough language. Going down below, let's see, the density of the Petri dish modeled by this function is this. The average value, yeah, that's given. That's a definite integral. Over here, this is also given 9.875. Yeah, they just give a few decimal places. The key idea is that you should only really round once, and you should round at the end. And in terms of the rounding, it can either be true rounding or truncation to the thousandth place, and then you'll be fine. Uh, Over here, yeah, everything's correct, but again, I almost missed it simply because I put a square as opposed to cubed, and that would have been a kind of fat finger mistake. But let me see what happens down here. First point is earned for a definite integral, so would have gotten at least the definite integral point. Presentation of a numerical value is not required to earn the second point. This can be earned by the average value setup. So as long as I set up the average value, thank you, I would have gotten the second point. But again, I would have just missed the third because wouldn't have gotten that value. So third point cannot be earned without the second. And so you actually need to have this. Uh, a response that does not provide the average value setup but presents an average value of this is using degree mode on their calculator. This response would not earn the second point, but would earn the third point for an answer of 2.5. Oh, fascinating. So again, if you use degree mode, just be careful. When you're actually on the test, you should set it to radians and just not fall for this kind of mistake. Okay. But the mistake that I almost made was that I interpreted a cubed as a squared, and that would be really, really bad. There's really no saving. But luckily, I read the problem again. So there you go, problem one.